Okay, so let me continue. And as I said, we have talked about machine learning in concepts. We have talked about machine learning in theories. And one of the most important theory to me is the bias-variance trade-off, right? Which says that we know machine learning is not about fitting observed data points. It's about making predictions for unobserved data points. So in that sense, we could look at the expected error, right? So the expected error on the test data. But where is that expectation coming from? The expectation is based on the fact that our training data, the observed data, could be sampled from a distribution, right? So we draw samples from that distribution. So if we calculate the expected value of the generalization error, okay? The error is the mean squared error. If you're doing regression, it's the generalization error because the error was evaluated on the test set, right? And it's expected generalization error because that was expected or averaged over the distribution of the training set, right? So we derived that. Again, I recommend you to look at the derivation and try to do that by yourself. It should be straightforward. That you will see that there are three terms. One is squared bias, and one is the variance, and one is uncertainty in the measurement that we cannot control. So if you want to reduce the generalization error, we can try to reduce the sum of the first two terms, right? But in the meantime, it's just too idealistic and actually impossible to reduce both simultaneously. I asked you to look at the theory behind it. Have you taken a look at it? Have you? Yeah, the Cramer-Rao inequality, right, which is relating the variance, right, to the information, right? So I strongly recommend you to look into that. That actually tells you why there is a trade-off, right? So then, in reality, right, we can make our models, right, significantly reduce the variance part while sacrificing the bias a little bit, right? Right? How do we do that? Well, if you make the model a little bit regularized in its complexity, right? Then the bias, the complexity decreases, the bias increases, but hopefully the variance decreases much faster, right? And we also introduced how do you quantify the model complexity, right? Which is not only determined by the model, but actually also determined by the data, right? So we used what method did we use to quantify? The shrinkage method, the LP norm, right? So that can be used as a penalty in your loss function so that you can simultaneously do the minimization of the loss to the observed data and reducing the model complexity simultaneously, right? So those are the theoretical concepts that are very important, and we're actually going to connect to them again, right? But today we're going to focus on practical machine learning. Again, just like what I said in the case of the optimization, actually you want to have a theoretical guideline when you are developing or even choosing optimization algorithms, right? You actually have seen that when the LP norm is L2, it's actually a very simple optimization problem if the loss is mean squared error. You actually have an analytical expression of the mean squared error plus L2 norm, right? If it's L1 norm, well, it's a little bit more complicated. It's still convex, but there's no smooth gradient anymore, right? And then in that case, there are still algorithms, right? Just not gradient-based algorithms. And then if the P is between 0 and 1, then it's even more difficult. It's non-convex, right? But if P is less than or equal to 1, in general, you have the benefit of having the sparse solutions. So you actually have to decide, right, a lot of things depending on your goals, right? How you choose the loss function and how do you do the regularization, okay? So we'll connect with those a little bit, but today, we'd like to talk about machine learning in practice, okay? This is largely based on the great slides, advice for applying machine learning from Andrew, okay? I think it was used to shared somewhere. Probably change the link and somewhere, but I thought this is very useful, so I'd like to talk about it a little bit, okay? So I'm going to start with, whether it's machine learning or deep learning in future, I think these are very useful. So I'm going to start with a classification machine learning model, right, that I haven't talked about, but hear me out so that, you can get it, right? So previously, you remember that we use, for instance, a linear classifier, right? W transpose times X. If X also include feature 1, then that corresponding W is W naught, right? So then there is a linear decision boundary, right? And then we have a linear classifier, right? Okay, so that's what we have seen before, okay? So in the case of the logistic regression compared to the linear regression, sorry, not linear regression, linear classifier, okay, sorry. So in the case of the logistic regression, we still have a linear decision boundary, but that linear decision boundary is not about the score of each sample, okay? So previously, you have a score of each sample, W transpose times X, okay? But here, I still have W transpose times X, but it's not about the score, okay? It's about the log odds, okay? So this is a log of the odds. What is an odd? Odd is the probability of y equal to 1 given x divided by probability of y equal to 0 given x. So log odds, okay? So the log odds is approximated by a linear decision boundary equal to 0, okay? And then if you know that the numerator and denominator add up to 1, right? Because that's one of the three principles or three laws of probability, right? Normalization. Then you can calculate P of y equal to 1 given x, the conditional probability that a sample x belong to class 1, right? And then you will find that it's a logistic function of this form, okay? So sometimes people also write it as sigma of this function, of this linear function, right? Right? So as a reminder, the logistic function is like sigma of x equal to 1 over 1 plus e to minus x, okay? So you replace the x by this linear function in the logistic. So that's the name logistic regression is coming from, okay? So you still have a linear function, but it's no longer the decision boundary in the score space, but it's a decision boundary in the log odds space, okay? So if you rewrite the probability, then you will find that it's actually a logistic function. So in that sense, it's called a logistic regression, okay? Right? You are regressing the log odds, and the probabilities are a logistic function of a linear function, okay? Of course, you can generalize it to nonlinear cases and so on, okay? If we look at a logistic function just to have intuition, right? So if we have sigma of x, that's a blue curve, right? So when x equal to 0, you should reach 1 over 2, right? 0.5, like this point, right? When x is 0, you should reach 0.5. So if you replace x by 2x, then you have this cyan curve, which still pass 0, 1/2, but it's getting like steeper transitions, right? This S shape is having steeper transitions. If you replace this x by x minus 2, then this is like what you learned in the signals and systems, right? It's like what? Is just affine transformation on time, right? So this is what? This is -2. So this is moving to the left or to the right. Sigma of x minus 2 relative to sigma of x is moving to the right. So it's advance, right? It's time advance, right? If you think about x as time. Then if you have the combination, which is the affine transformation of x, which is linear transformation, then in this case you have this red one, so it's going to be shifted to left or right by how much? 0.5x plus 1. So 0.5x compared to 2x, it's expanded, right? So the signal is expanded, right? So that's why compared to the blue, it's like stretched the left and the right, it's expanded. It is because 0.5x plus 2. And then it's expanded and then also shifted to the left, right? By 2 units, right? Depending on whether you shift or scale first, right? But if you follow one convention, you're moving left by 2 units, okay? It's 0.5 times x plus 2, right? So these are the decision boundary of, so in this way you can see that depending on your learned W, right, you have the different logistic function, okay? Okay, now let's rewrite what we had here before, but put a subscript I as the index of the training example, okay? And we also have a semicolon here to indicate what's behind the semicolon is a parameter, okay? So it's a parameter. So in this case, we're asking what's the conditional probability of example I being in class 1 or 0, given the features xi, and of course the parameter w, okay? So based on our defined decision boundary, we can find that it's just a sigma function of this linear function, okay? It's a logistic in this linear function, all right? Okay, so then, and then in this case, now we have to ask ourselves, right? So if you have defined a new classifier, right? In the past, I understand that you used this linear classifier in the score space, and your goal was to intuitively maximize the margin, right? And we derived, well, I didn't fully derive it, but I hope you have tried it, right? I gave the hints. We derived that the margin was proportional to 1 over the norm of W, right? And then we can equivalently minimize the norm squared, L2 norm squared of W, right? But in this case, if you want to find the best W, given a set of examples I from 1 to n, what would be your loss function? What is an appropriate loss function? What is an appropriate loss function here? You are trying to adjust W for the given n training examples of paired xi, yi, where I goes from 1 to n, so that some loss is optimized. What is that loss in this case? Right? See, we are looking at the probabilities now, okay? Yes. What is an appropriate loss function here? You must know, don't be shy. What I wrote there? Actually, it's one step before that, actually. What I wrote here was already following some assumptions. Okay? So what is the probability that you're trying to optimize here? the probability of all the y1 through yi through yn, given all the xi, I from 1 to n, semicolon w. Is that right? The probability of observing all the y given all the x and w, right? That is the principle. Is that right? Now, if I assume these training examples are IID, identically and independently distributed, then I can factorize that conditional probability into the product of all these p's, right? Am I right? Don't know what I touched, but it looks very... Do we agree? So then, the probability of the vector y given the vector x and w, where by vector I mean y equal to y1 through y2 through yi through yn, and x vector is x1 through xn, right? So that conditional probability can be now factorized as the product of all these p of yi given xi and w, right? Then you have then you can, of course, maximize the product of the p, right? Or you can maximize the log of the product of the p, right? Which is equivalent. And then if you maximize the log of the product, then you are maximizing the sum of the log probability, right? So you have to start with the principle. So I know I put, the final step there, but that's not where things started, right? Okay. If we agree on that, then we can focus on what's behind the summation, because for every example I, what's behind is the same, right? Okay. Then how do we write this log of p, right? So this is something just like the what we did in the support vector machine, remember? We had two kinds of constraints, right? Whether you're blue or red points, depending on which side of the decision boundary you are, right? Your score may be bigger than or less than that threshold, right? But we united them together into one constraint using yi, right? So here it's the same. So we are using yi here. So if yi is equal to 1, it's log of these probability, right? If yi is 0, then only, if yi is 1, then only the first term is non-zero, and the second term is going to be 0, and the first term is nothing but the probability of yi equal to 1, given xi and w, right here. If y equal to 0, then only the second term is non-zero, and what we have here is exactly log of the probability of yi equal to 0, given xi and w. So that's what we have here. Okay? Okay? So that's what we have here. Okay? So this is... So what's the relationship between what I write here and binary cross entropy? You must be using my binary cross entropy somewhere, right? So what's the relationship between what I wrote here and the binary cross entropy? Can someone try? How many of you have used binary cross entropy? You must have used it. No? Binary cross entropy? If you use classification, if you do any classification, you must use it, right? Okay, so I recommend you to look into that and see what's the relationship with this one and gain a better understanding, okay? So again, this is just a background, okay? So this is a baseline model, right, that I start with. So my question is, how do I diagnose, okay? All right, so I have a model like this, right? And I apply this model to, as you know, one of the early application of machine learning, okay, not deep learning, machine learning. That is spam detection, okay? Nowadays, most of the email probably actually all of the email providers also give you this spam detection, right, automatically. Sometimes it does make mistake, right? By the way, which one annoys you more? False positives or false negatives? If I have a spam detector, it's a classifier, machine learning classifier. Which one annoys you more? Because that matters in how I train my classifier, right? Are you annoyed more by the false positives? Yes, or false negatives. You are more annoyed by the false positives. You're more worried about missing important emails than get bothered by probably 5 more just spam emails that just got escaped, right? Probably. Okay, so then we may have to think about what is the loss function then, okay? So let's say that this is a very simple case in the early days, right? That you have a small set of 100 words to use as features, okay? In this case, we use Bayesian logistic regression, okay? And we are using gradient descent to optimize this loss function, right? And we found 20% test error, which is unacceptably high, okay? Again, so in our case, we are maximizing the minus loss, which is minimizing the loss, right? This is what you have seen before. And also, we are regularizing this model complexity, right? Here, this model parameter is theta, right? Okay, and I have m training examples, okay? So, and also, just, you may wonder, well, why did I have to use gradient descent? There is a unique global optimum for the maximum likelihood prediction under the logistic regression, but this is the same like, mean squared error with lasso, L1 penalty, right? There is a unique global optimum, but in that case, there's no gradient method that optimizer that works because of the smoothness issue. In this case, there's also no closed form solution, but luckily you can still use a gradient descent to solve the problem. Okay. Okay. So we sometimes use the W before, right? Here we are using theta here, so please don't be confused. Okay. All right, so what do you do next, right? So that is possible, right? Even nowadays, right? When we are using a lot of fancier method, whether it's some kind of deep learning, right? The only difference is now your data is bigger. And the cost of evaluating the model performance as well as the cost to improve the model performance are also increasing, actually. So that just makes diagnosis even more important, right? So let's use this example to see how we diagnose, right? Okay, so let's see. What do you do? How do you diagnose, right? So let's ask a similar question, right? So if you found some problems, right? Some random noise or some issues of your car, right? What do you do, right? So there might be different scenario, but usually you send it to a checkup, right? A diagnosis. What you don't do, what you never do is try to replace every part one by one and eventually see whether it works or not. You never do that, right? Because the cost is unreasonable, but more importantly, the practice is not reasonable, right? But the funny thing is that if you talk about our research, especially diagnosing, sorry, I shouldn't use that word, improving our machine learning models' performance, what we don't realize is that we are much more often doing something like that. We start with this model, we see, oh, the performance is not good, then we try everything we can. We try everything we can and then hope that the performance will increase, right? So like in this case, right? So you can try getting more training examples, right? You can use the same training example but try bootstrapping, right? You can use a smaller set of features, you can use a larger set of features, right? Or you just change the features, right? For instance, you feel like maybe the words from the email header or is more implicative, right? Or the ones in the email bodies can be more implicative, right? And then you think that, well, I'm solving an optimization problem. Maybe I can run the gradient descent for more iterations so that I can get a better quality optimum, right? And then you realize that, oh, I learned all these great theories about the iterative optimizers, right? We learned that the steepest descent was simple but slow. So maybe I can try Newton's method. Sorry, it's simple but fast, right? Well, no, I take it back. It's simple, and every step you just take small amount of calculations, but it's going to take a lot of steps because convergence rate is slow, right? And then you figure that, well, maybe I can try Newton's method, right? Each step, iteration, I spend more time calculating, including the second order, right? Information, but maybe I can take less steps, right? And what else? I can try the different lambda, right? I can try different lambda, or I just use the support vector machine instead of this Bayesian logistic regression, okay? These are all possible, but the question is, just like the case of the car, right? Would you just try all of them? Or just try them one by one? Or what's the order you're going to take? Any suggestions? These are all things we can try. How are you going to decide? Apparently, we can do all of them. It's just going to take much longer time, right? But if you cannot afford doing all of them, or more importantly, you want to be rationally satisfied instead of trying everything possible, what would you do? Just like what you do with your cars. You send it to a body shop for a diagnosis first. In other words, you have to figure out what's the problem first. I know you say that, oh, no, I know the problem. The problem is that the test error is high. Yes, that is the final, ultimate symptom. But what was the problem? Okay, what's the disease that caused the symptom? That's the question I'm trying to ask. You need to figure out what's the problem, okay? Okay, so the better approach is, as I said, you try to run diagnosis to figure out what the problem is and then fix that problem. Exactly, okay? So in this case, let's say we start with a problem that is very, superficial, just the phenomena that the test error is 20% unacceptably high, right? So then you have to start with some hypothesis, right? So one hypothesis we have learned before was the overfitting versus underfitting, right? We learned before one perspective, that is bias-variance trade-off, right? I think you can use that as one of your ways to diagnose. Remember, there are so many different ways of diagnosing, and this is just one way to diagnose. And then each diagnosis is actually following some theoretical foundations, right? Here, you might wonder, well, based on what I know about the bias-variance trade-off, in my case, am I experiencing the high variance issue that's overfitting, or it's probably high bias issue, right? Right? So that's one way, right? So then we can follow this direction and do diagnosis, right? The diagnosis is look at the variance and the bias, okay? So the diagnostic, in the case of the variance, you're going to compare this training error with the validation error, right? In the case of the bias, you can also look at your training error and whether itself is bad or not, right? In the case of the variance, you can compare the error for the training set and the validation set, right? See how this model behaves differently, how the predictions behave differently for different data sets. That's what the variance is about, right? Bias is about how off the prediction is compared to the actual, right? So you can look at the value of the training error or the validation error itself, right? Rather than comparing the two, right? Okay, so we actually have already compared, we have already discussed this before, remember? In this case, we have an underlying green function that is not known, but observed with the noisy observations, which are the blue circles, right? So if you use a overly complex model, like ninth order polynomial, you can fit all the blue circles perfectly, but it's of high variance, right? Right? So if imagine that these blue circles, any of them just move a tiny bit, then your circles would, then your red function will just change drastically, right? So that's overfitting, okay? So now let's look at a illustration here, okay? So this is like a dartboard, right? This is like a dartboard, right? So what you're trying to do, right? You're throwing the dart to the dartboard, and let's say this is the center, right? Is perfect, right? It's a perfect machine learning model like this green function. You're getting the ground truth. Okay, let's say that's what it corresponds to. Okay. And then let's imagine that as your data changes, your training data changes, every time your trained machine learning model is gonna give a performance, right? It's like, this every time you throw the dart to the board, right? So it's gonna land somewhere, right? It's gonna land somewhere. And the landing points, right, are if we just compare among the landing points, it's like comparing the model predictions, right? So the ideal case is that these landing points are close to each other, meaning that the model predictions are close to each other, low variance, right? But in the meantime, they are all close to the origin, right? Right? Low bias, right? So in other words, the model predictions differ from each other very lowly, and their error is very low, the distance to the origin, okay? So this is ideal, a low bias and a low variance, right? But unfortunately, we don't often see that. What often happens is, like in this case, right? In this case, if you look at these model predictions, right, they're actually not, well, in this case, at least we can see that they are far away from each other. They are scattered from each other. Right? The model predictions are very different from each other as the data changes. That means it's high variance, isn't it? But in the meantime, they are not too far away from the origin, right? They're far away from each other, but not far away from the ground truth. And their average might be even unbiased, actually. So in that case, it's low bias, but high variance, right? Another scenario is that these landing points are all close to each other, meaning it's low variance, but they are all far away from the ground truth label. So in that case, it's high bias, right? But of course, sometimes what's breaking you is that, like in this case, right? So your model predictions are far away from each other, indicating a high variance. In the meantime, they're all far away from the ground truth, indicating a high bias as well, right? So this is one kind of diagnosis you can perform, that is looking at whether your problem is overfitting or underfitting, right? So you know what to do when there's overfitting, right? You know what to do if there's overfitting. What do we do if there's overfitting? If it's overfitting, that means model is too complex, so we can do what? We can reduce the model complexity by regularization. We can also use ensemble methods to reduce the variance, right? So that's what we have learned. But now, let's make this diagnosis a little bit more concrete, because this is an illustration. This is the illustration, right, which is very intuitive, right? But let's make it more concrete, right? Let's make it more concrete, okay? So let me first repeat that. Now we're looking at the diagnostics of machine learning algorithms, okay? So don't ask, why isn't my machine learning working? Or, why is this test error that high? The right question is, what could be the problem and how could I diagnose? And if I determine the cause, how would I change the model, right? Okay, so the one right, the correct mentality is let's use diagnostics to figure out what's the problem and then fix them correspondingly. One kind of diagnostics is, as I said, is to figure out whether it's underfitting, overfitting, or maybe just doing fine. Okay, this is just one diagnostic. There are other diagnostics as well, okay? So in this case, we are trying to figure out whether it's underfitting, overfitting, or probably both, right? Then we can compare, for instance, the training error and the validation error, right? Right? So if both errors are high, that means probably a high bias underfitting issue, right? If the training error is low, but the validation error is high, right? You might be experiencing the high variance issue, which is overfitting, okay? By the way, you have to be careful. In reality, is your training set and the validation set from the same distribution or not, right? Because I have seen sometimes people actually use a much more challenging validation set, then they found that the performance of validation set is so bad. Then, maybe that really prevents you from the diagnostics, because here, this diagnostic is assuming that training and the validation data are from the same distribution, okay? Right? Otherwise, the validation set is going to be in a target domain that's very different from the origin domain. Then there is a transfer error, of course, right? So then we cannot just draw that conclusion that easily, right? And a good case, of course, is training error is low and the validation error is just a little bit higher, right? That's a good fit, right? So that's a good thing. So now let's try to see that, right? So let's see, right? Let's say there is let's look at this error level, right? What I'm changing here is the size of the training set, okay? And let's say that there is ideal desired performance like here. This is like the center of the dartboard you want to land in, okay? That's ideal case. Okay, so let's see in this case, right? As the training set size increases, the test, the training error and the test error are both getting closer to the desired performance, okay? Please don't get confused. I'm not saying that training error is increasing, okay? So this is like the approaching this desired performance from both directions, okay? So in other words, as the training set size increases, right? So both are getting closer to the desired performance, right? But what you see here is the following, that the training error is much smaller compared to the test error, right? Or in our case, I would rather call it a validation or development error, right? Because I usually do the test set evaluation in the end. We don't, we just deploy the trained model once. So usually I look at the validation error instead, okay? All right, so in this case, the training error is low and the validation error is high, so we call it a typical high variance issue, right? So in this case, we see that if we keep increasing the training set size, it may help because after all, test error is decreasing, right? Just slower than training error does. So if you keep increasing the training set size, right, it can still help. But there is still, this gap may get saturated. So you need to do something. Okay, we'll talk about something later. Another case is like this, right? So in this case, there's not too much difference, actually, as the training set size increases between the training and the validation set error. That is good, but unfortunately, both are unacceptably high from the desired performance. So if that's the case, it's a typical high bias, right? Because the variance is low, but the bias is high. So these are the diagnoses you can look at, right? So in practice, sometimes people actually don't change the training set size a lot sometimes, but still you can even do the diagnosis during the training, right? You can look at the errors over epochs even during training. So now, once you figure out, right, the problem, now you can choose the fixes accordingly, okay? So as I said, if you want to fix the high variance, you might want to get more training examples, right? So, but remember, this is only to fix a high variance, right? And a smaller set of features is what? Is reducing the model complexity, right? So it also fixes a high variance, right? If you use a larger set of the features, right, to some extent it's increasing the model complexity. You may fix a high bias issue, or you are using the email header features using more informative features, right? In this case, you can also fix a high bias issue, right? So as you can see, this is what you will do after you figure out what's the problem, right? You wouldn't try all of them, would you, right? Okay, then you ask, well, what about the remainder? Well, the remainder are fixes that have nothing to do with the first diagnostic we talked about, because the first diagnostic is only about overfitting or underfitting. Okay, we haven't talked about other diagnostics yet. What other diagnostic? Don't forget that we're solving an optimization problem, right? Right? So one question you have to ask is, if I'm optimizing the right function, is my optimization algorithm converging? Okay, let's say I'm optimizing the right function, but is it converging? Right? Did I report a converging solution? Right? So in other words, it's optimizer's convergence issue, or maybe I'm not even optimizing the right function, right? So in other words, you have to figure out, previously the diagnostic is about your model performance, whether it's high variance or high bias. Then this diagnostic is about optimization, formulation, and algorithm, right? So let's try to figure out both, right? Whether your formulation is correct, the choice of the loss function is agreeing with what you want, right? And if that's the case, whether the optimizer is doing the right thing to get the optimal parameters, okay? Okay, so first of all, let's ask what we care about for this spam detection, right? So as I was asking you earlier, right, do you care about the false positives or false negatives more, right? But in general, we can say that there is probably an assessment, right, like an indicator, right, which is a weighted sum of all these indicator functions, right? Right? So this is when the predicted is agreeing with the actual email label, right? We can also try to maximize this one, right? Or we can try to minimize when this equality changes to inequality, right? But depending on the Y being the spam or non-spam, we may want to give different weights to that correct decision, right? Right? So in other words, you may care about this one, this measurement that is more reflecting the actual performance of this spam detection. Okay. By the way, this is not always the loss function you use. Okay, because you see in the different machine learning models, they have different principles and different loss functions. Whether it's maximum margin, I'm talking about classifiers for now, or in this case, the maximum likelihood, or the maximum posterior, right? So there are different principles, right? And those principles determine the loss function, but they don't have to be actually the performance evaluator. So maybe in this case, you care about the performance that can be evaluated in this way, okay? All right, so now let's look at the following, okay? Let's try to figure out whether it's a formulation issue or optimizer issue, okay? Okay. We first can figure out whether it's a formulation issue, right? For instance, you wondered whether I should use support vector machine, right? Versus a Bayesian logistic regression, right? Let's assume that for each model, the formulation is already correct in the sense that you have taken care of this lambda or c, these hyperparameters, okay? So for each formulation, the corresponding hyperparameters is already taken care of. Let's assume that, okay? Once you have that, right, because you see that these different formulations are different, right? Bayesian logistic regression is maximizing this J, right? And then support vector machine is minimizing this 1 over the squared margin, right? Plus the slack variables for the soft, right? So now, okay, so then let's see. First, let's say the support vector machine give you a parameter theta SVM, and Bayesian logistic regression give you the parameter theta BRR, okay? You can ask yourself, which one performs better in the eyes of the weighted accuracy that you care about, okay? You can plug in these two models and ask which one has better performance, right? Okay, let's say that you found actually support vector machine even does better in the sense of this performance evaluation than Bayesian logistic regression, okay? Well, then you ask the following. Is my Bayesian logistic regression performing worse than support vector machine because it's Bayesian logistic regression, or because I actually didn't optimize this Bayesian logistic regression problem? Okay? Right? I didn't find the optimal. So this is, right? So to answer this question, right, you can compare both support vector machine and Bayesian logistic regression in the same objective function as the Bayesian logistic regression, J. Okay? Remember, Bayesian logistic regression is trying to maximize that J, right? That's the battlefield of Bayesian logistic regression. If your support vector machine's answer is even better than the Bayesian logistic regression in its own battlefield, the loss function that BRR is trying to maximize, that means what? The optimization algorithm or optimizer did not give us an optimal solution, or far from it, right? Because we were trying to maximize J, but actually when our optimizer trying to maximize for J, actually it's worse than support vector machine, which is trying to optimize for something else, but it turned out to be even better. Also also evaluated in J, is that right? Right? So it's like you pick the high jump champion, right? And then compete with you on the 100-meter track, and then actually he or she outperforms you. Then you may wonder whether your race of the 100-meter was competitive enough, right? So you need a better optimizer. So that's one issue, right? So in the case one, as I said, that support vector machine has better performance in our performance assessment, and it even beat the BRR in its own track, in its own loss function, right? So that means our optimization for the Bayesian logistic regression failed to maximize J, far from it, right? So the problem is now with the convergence of the optimizer, right? Right? So that's one possibility, right? The other possibility is that, yeah, support vector machine is better than BRR in the performance we care. But its solution is not necessarily better than BRR in the track of BRR. In other words, if we evaluate these two both in J, this loss function of BRR, BRR is still better. Supported vector machines model are not necessarily better. Okay? So this means that probably, right? I'm not saying there's guaranteed no issue with optimizer, but so far there's nothing suspicious about the optimizer. There's more issues similarly with the loss function similarly, right? Because because supported vector machine apparently use a different loss function, right? And it's not better than the BRR in J, this optimal solution. But the supported vector machine chosen by its own margin maximization performed better, right? So this means that probably in this case, supported vector machine is a better formulation, optimization formulation than Bayesian logistic regression, isn't it? Right? So this means that maybe the J of theta with this Bayesian logistic regression, right, is probably the wrong function to maximize, and what you care about is A of theta, then the loss function of supported vector machine may agree with your A of theta closer, okay? Then you may wonder, well, if I care about A of theta, why don't I directly optimize A of theta in training my model? That's a complicated question, right? First of all, not all of such A of theta can be easily analytically expressed and then solved by gradient algorithms, right? But it's half and half. One example of is area under the precision recall curve, right? If you try to maximize the area under the precision recall curve, you rarely see that directly goes into the loss function of training your classifier, right? But now people are developing better and better algorithms so that you can have surrogate functions who are easy to optimize, but whose optimality more or less aligns with the optimum area under the precision recall curve. Okay, that's a possibility, okay? But it still remains a challenge. The second one is that different models have their different assumptions, right? So they not necessarily all agree with this performance measure you care about, A of theta, right? So sometimes as a trade-off, some people just use A of theta as the validation assessment. So when you choose the hyperparameters, you evaluate A of theta on the validation set, and then that's something that people do, right? But there are all kinds of possibilities. But so far, let's come back to the second diagnostic. It's about the optimization, right? Whether we are looking at the correct optimization formulation or objective, or are we using the correct optimizer or optimization algorithm, right? So if it's an algorithm issue, then I probably should make it more likely to converge, like run it more iterations or try Newton's method, right? In the case of the deep learning, you may use different methods, right? Change stochastic descent to atom or even something more sophisticated, right? Because why? Because atom use more information like momentum, right, than stochastic descent. You can also try a more sophisticated algorithm, like in the low-dimensional case, you can try Newton's method, but in the deep learning, as I said, you may consider like atom and others that use second-order information or momentum or more information than gradients, right? If it's an objective issue, maybe your lambda was an issue, okay? I previously said I hope your lambda was fine, but probably your lambda is an issue, okay? But if your lambda is not the issue, then maybe you should change the loss function and the model totally, right? So in this case, probably changing it to a supported vector machine, which is actually agreeing with your performance metric even more. Any question? So now that you see, we have two kinds of diagnostics, right? One is about the model behavior, right? From the perspective of bias and the variance. One is from the optimization, right? From the perspective algorithm and objective or formulation, right? So depending on the outcome of each diagnostic, we can choose the corresponding fixes, right? So in other words, what you do is, starting from the far right, there's something called diagnostic. Based on the diagnostic, you figure out that I want to fix a high variance or high bias or optimization algorithms or optimization objective, and then you decide to use one of them. Okay, so that's the direction. It's not the other way around, that you try all the possible fixes and write all of them down and then try all of them, right? Okay, just some summary of the quick fixes, right? For the high variance, we can try more examples, but if you cannot afford it, try bagging, right? And then try less features, right? Try regularization, right? If you try to fix a high bias, you may want to try a larger set of features with more information, right? That usually is the case. I have seen so many papers focusing on the deep learning architecture so much. They introduce very sophisticated architecture, but there are two scenarios, okay? Two possibilities. One possibility is that their performance did improve compared to the state of art, but not really because of the architecture, but because of their features were much more indicative and informative. That's one possibility. The second possibility is that they tried a lot of things, but they just cannot beat the state of art. And maybe somewhere here they're doing slightly better, but there, it's like roughly the same. Then people ask, why bother trying so many things, right? And very often they just forget about easy, well, it's conceptually easy, just practically difficult thing. That is, come up with smart features. I know everybody is talking about end-to-end, as if you can stack the original raw data into the input end and then hope the output end will give you the perfect solution when you train the model enough. That does not happen that way. Actually, you still have to spend a lot of time on features, right? But that is painful for people who are not familiar with the domain knowledge, right? Right? If you just treat the protein sequence as an alphabet of, as a text written in an alphabet of 20 letters, that's super easy. But if I ask you to do, well, what about the position-specific sequence, position-specific scoring matrix or profile? Then you need to do the multiple sequence alignment and construct those, and there are other kind of things, right? That you may figure that, that's too much painful, right? But we really need to, pay attention to this issue, because very often what I see is that our models are both high variance and high bias, and the high variance is easier to treat actually. The high bias, you actually need more information from the domain. That's an issue, okay? And then sometimes it's about the optimizer, right? The objective function and the optimization algorithms, okay? And this was where I downloaded before, but I think the link might have been changed, and maybe the slides were even taken away. So let's see whether that still works. You may not be able to directly click it, because sometimes this hyphen, when converted into the HTTP URL link, it gets into a different format or something. So it becomes a different ASCII character. So if you click it directly, you may not get it, okay? But usually if you change that weird ASCII character into a hyphen, you should be able to get it, okay? So this is about the diagnosis, okay? Another thing I want to say is two kind of analysis of your models, okay? Let's say you have your model, and you want to understand your model behavior, and you want to improve your model behavior. And so these are two things that we will try to figure out. So what you can do is two directions, right? You can start with your model and look at different components and replace each component with the most ideal scenario and see whether that helps a lot or not, right? Then you figure out, oh, maybe I need to pay more attention to this component. So that's called the error analysis, okay? The error analysis is about what if I change each component to much better scenario? Does that improve the performance a lot or not? Okay? If that is the case, then I'm going to spend more time on this component. Okay? Another kind of analysis is what you often do called ablation study. So in the case of the ablation study, right, you start with, again, with your baseline model, right, with different components, and you are saying that, well, let me take away the good contributions I made to each component and see how much worse the performance becomes, okay? In that way, I can also delineate, right, or isolate the contributions from each individual components. So both are important, right? One is about how to move forward. One is how to explain that what you introduced actually worked, okay? But they're just opposite directions in some sense, okay? So now let's see, you have a machine learning model with a pipeline, right? So let's say this is face recognition, right? It's a much easier problem nowadays. There's a camera image, you have to pre-process it, like removing background, and then you have to detect the face, and then you need to do the segmentation, figuring out which pixels correspond to eyes, nose, mouth. And then you may end up having using this as features to a machine learning model and then predict the label. Okay? So this is a very easy case. Now, you see that this is actually a very sophisticated machine learning pipeline already, and that's often the case, right? So let's see. The error analysis basically asks how much error is attributable to each of the components. Okay? So it's basically asking, how much error is attributable to each component. So in this case, as I said, for each component, you can plug in the ground truth because the most ideal component here is to give you the exact ground truth, right? Right? For instance, it's giving me the face detection perfectly, right? In reality, your pre-processing may not give you the ideal input, or your face detection may not give you the perfect face detection, okay? But let's say that I replace each component with the ground truth, okay? If that's the best you can do, how does the accuracy changes, okay? For instance, in this case, right, the overall system is 85%. If I do the pre-processing, right, perfectly, like expert, just manually remove the background, for instance, you see the accuracy only increased by 0.1%. Okay, that means, all right, stop there. You don't need to spend more time on background pre-processing anymore, okay? But if it's a face detection, let's say, I always detect a face successfully without any error and then pass to the downstream components, then you see the accuracy increase to 91%. Great, that's something I can improve, right? And then let's say, starting from whatever the imperfect face detection, right? I think in this case it's probably, let's see, is it cumulative? The numbers look increasing, but I think we are plugging this individually, but do you think that in this case, eyes segmentation, we definitely plug in the ground truth for the eyes segmentation, but do you think we keep the ground truth for the face detection from the early stage or not? Based on the numbers, it probably is the case. I cannot tell for sure, okay? But it makes sense to say that let me incrementally add things one by one. But usually I do have these individual perturbations, like the marginal perturbations. I do perturb each one separately without incrementally, okay? You could have another lineage of incremental, like the ablation study, you could incrementally reduce more and more components, but usually you will also leave some other combinations, right? Like I just remove any one of these components, right? And then starting from one of them, I incrementally remove more and more. So in this case, we see that eye segmentation, nose segmentation, and mouth segmentation, let's assume that these are just plugging in the corresponding ground truth alone without changing the other parts, okay? So it looks like if that's the case, the most room for improvement is in face detection and eyes segmentation. If that's the conclusion, then I think they are doing this incrementally, right? If that's the conclusion. Because they figured out, oh, after adding the face detection perfectly, I increased 6%, and then another jump, 4%, is on top of the perfect face detection, I add the perfect eyes segmentation. So this one is incremental. Okay, is this clear? So that means what? You want to spend more time on face detection and eyes segmentation and improve those components, right? You can save your efforts and maximize your outcome. So this is what error analysis does if you want to improve your method. Ablation analysis is trying to explain why your current model is behaving like that, okay? So error analysis is explain the difference between the current performance and the perfect performance, right? What if I replace the individual components by the perfect ground truth? Ablation analysis is trying to explain the difference between your current performance and some baseline. When you remove some good properties of that component, right? So for instance, if you build an anti-spam, right? On top of this logistic regression, you also have these clever contributions, right? You say that, well, these are my major contributions, right? In the end, when I have all these contributions together, I did improve compared to state of the art by 10%, right? But then the question is, you know, how much did each of these components actually help, right? So in other words, you want to remove some feature in quotation. I don't mean the input feature. I mean the properties of the algorithm and see the impact to the performance, right? So in this case, it's probably incrementally removing the components, right? The reason I think incremental adding or removing is tricky is because the order may not be that clear. So sometimes when we have few contributions or components, we usually have to combine the incremental and the individual, you know, any one or any two sometimes even. So in this case, let's say the accuracy is already 99.9%. If we remove our contribution to the spelling correction, right? So the spelling correction. If we don't do spelling correction, the accuracy is 99.0. If we don't include features from the sender host, the accuracy drops to 98.9. But you know, you keep dropping the major contributions that you introduced and that separates you from the baseline or state of the art, then you see that eventually it drops to 94.0, okay? This is also a good idea sometimes when your implementation is different from the baseline, right? Sometimes you had to use your own implementation. You cannot change the baseline repo for your own contribution, right? So in that case, you definitely want to do the ablation study all the way see here whether the performance agree with the published baseline performance. Because it's possible that your implementation had some faulty issue and you realize that I'm always like 80% here compared to the baseline, right? Which is 82%. What was wrong? Then you keep ablating your features and realize that, oh, if I remove all my contributions, my accuracy is only 70%, right? Then why is my implementation of the baseline so different from the reported baseline? So there must be some implementation issue as well. So that's another reason I like this kind of ablation study, right? Because you think conceptually, if I make these contributions, they should help, right? But if you remove all of them, you cannot even replicate the baseline, then that means some implementation issues are there, okay? And in this case, we can conclude where the biggest job was here, 98.9 to 95%, right? So it looks like the email text parser features are most important, seemingly, right? So, and I think now it's almost a standard that you need to include ablation study in your paper to show that you understand or you have a proof that your major contributions actually had an impact of your performance improvement against the state of art, okay? So these are the two kinds of analysis. Again, error analysis and ablation study, okay? Again, during the development process, you may want to do some error analysis, trying to see how you can improve. But once you figure it out, you can do the ablation study, right? Usually in our research, what we do is the reverse ablation study. We start with a baseline, and we think that we have several ideas, and then we build upon this idea, build upon this baseline, and add these ideas one by one.